একটা কাজ করা যায়, ইউটিউবে লাইভ করে সেটা ইউটিউব থেকে চালান যায়। আমার তো না না এটা কানেক্টেড থাকো, ইউটিউবে লাইভ করে ইউটিউব চালাই দিও।
লাইভ হচ্ছে দেখো,
লাইভ হচ্ছে না। এটা বন্ধ।
মাইকটা অন আছে, তোমার মাইকটা অন আছে,
এটা বন্ধ করে
স্পিকার এই ফ্লোতে অন আছে, কারো কারো মাইক অন আছে। হচ্ছে হচ্ছে লাইভ হচ্ছে, কিন্তু শুরু হচ্ছে এরার নেটের কানেকশন ইউ লস।
আরে আমার
লাইভ কিন্তু হচ্ছে, যে যার নেটের করতে বলে লাইব্রেরি থেকে দিয়ে যায় সব। তাহলে আপনি লাইব্রেরি থেকে স্টার্ট করে দিতে হবে। এটাও এর থেকে পিক্সেলের থেকে চলছে, এটা স্পিড থাকার কথা। লাইভ আসছে না কেন? তুমি কলেজের নেটই তো হচ্ছে। আমার এখানে তো আসছে। একটু দেরি করে আসছে, কিন্তু আসছে। আপনার এখানে আসছে না, তোর এমনি করে দে, লাইভ টাইপ করার দরকার নেই, এমনি করে দে। ঠিক আছে, মোবাইলে হ্যাঁ হচ্ছে তো, হচ্ছে 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 নামটা চেঞ্জ করা হয়নি, লিঙ্কটা দিয়ে দাও, ম্যাডাম লিঙ্কটা দিয়ে দাও। যে কোনো একটা এর থেকে এবার কানেক্ট, এটা কার সাথে কানেক্টেড আছে? ম্যাডামে দিয়ে দাও, তুমি হোয়াটসঅ্যাপ, এটা কার সাথে কানেক্ট, হোয়াটসঅ্যাপে লিঙ্কটা দিয়ে দাও। এটা কার সাথে? তাহলে তোমার সাথে এটা চালাও। আমি চালাবো না, কি করে না পাই? ম্যাডাম দিয়ে দাও লিঙ্ক। আমি ওটা থেকে অফ করে দেনা তাহলে এটা থেকে ইয়েটা কোথায় আপনি লিঙ্কটা পাঠাচ্ছি তোমারটা থেকে কোনটা যে কোনো জ্যাকটা হচ্ছে তারটা থেকেই করো এই না না আমি অফ করে দিলাম এবার দুটো দেয় আপনার থেকে কানেক্ট করো দেখুন দেখুন আমার এখানে কানেক্ট আছে কানেক্ট করে যেগুলো একদম করো কানেক্ট করো দেখতে কানেক্ট করো না ব্লুটুথ অন করে কানেক্ট করবে তো অ্যাডাপ্টার বার আচ্ছা আমি লিংকটা পাঠিয়ে দিচ্ছি কানেক্ট হচ্ছে এবার ইউটিউবটা চালাও সাউন্ড দাও হ্যালো হ্যালো সাউন্ড দিচ্ছে না হ্যালো ইউটিউবে অন্য কিছু বাজাও হ্যালো ও অন্য কিছু একটা চালাও গান আছে ইউটিউবে গান চালালে আবার ওইটা নেই ইউটিউবে বাজে না তোমারটা অন কর এইটা দিয়ে হবে না বলছি তো এটা দিয়ে হবে আচ্ছা এটাতেও হবে এটাতেও হবে করো করো অ্যাভেন্টার বার কোথায় কোথায় এটা দেখি কানেক্ট করো অ্যাড ডিভাইস করো
বলো এইটার মধ্যে হচ্ছে মানে পেয়ার হওয়া হচ্ছে না কিন্তু মানে এর সাথে হচ্ছে না পেয়ার হ্যাঁ এই স্পিকার হ্যাঁ বললাম মানে পেয়ার হচ্ছে পেয়ার হচ্ছে
চালাও তুমি যে কোনো একটা চালাও
তাহলে কি এটা তোমার
আরেকটা ট্যাবই চালাও না
আচ্ছা এটা সাউন্ডটা তো কমানো তো বলে
সব ঠিক আছে
সাউন্ড
সব
কমানো
ঠিক আছে দাঁড়াও। এই stupid। চলছে সবাইকার সাথে এটার সাথে কানেকশনটা তো ইম্পর্টেন্ট
পেয়ার হচ্ছে কমানো হচ্ছে
দাঁড়াও দাঁড়াও যে কোনো একটা কানেক্ট হবে সবার সাথে একসাথে হয়েছে এটা এটা হয়েছে আপনি এখানে একটু বলুন আরে চালাও না এটা আবার এইটা চালিয়ে দিলেন এখন বললে দেরি হবে তো মানে এটা তো লেটে আসছে
Hello.
এখানে একটা দিতে গান টান কিছু নেই আচ্ছা বলছি এই যে দাঁড়া 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 সাউন্ড কমানো আছে হচ্ছে হচ্ছে আচ্ছা আচ্ছা এটা পুরো আপনাকে বলি এখন বললে হবে না তোমার 3-4 মিনিট পরে আসবে এটা স্ট্রিমিং তো এটা দিয়ে তুমি অন করে স্টার্ট করে দাও এখানে ওর থেকেই বসে করে ওর মোবাইল থেকে বসে অন্য লোক এখান থেকে তো এ আসবে তাহলে তোমার এখানে কি হবে না তোমার মানে ব্রেন ডিস্ট্রাক্ট হয়ে যাবে তোমার সাউন্ডটা দিতে হবে হ্যাঁ এবার হবে হ্যালো হ্যালো, এটা লাইভে রাখা একদম একটু লাইভে রাখ, টেনে দাও, টেনে দাও। হ্যালো, এটা কি তাহলে ইউটিউব চ্যানেলটাই দেবো আমি নাকি এটা দেবো? হ্যাঁ হ্যাঁ হ্যাঁ। দিশা দিশা তো দিশা দিশা স্যার, এটা চ্যানেলটা দিলাম। এই তোমরা সবাই একটু স্নান করো। এই ঘুমে দিকে জয়েন করো, সবাই ঘুমে দিকে জয়েন করো, ঘুমে দিকে জয়েন করো। ঘুমে দিকে জয়েন করে সাউন্ডটা একটু আস্তে রাখবে, সাউন্ডটা কমিয়ে রাখো সাউন্ড।
Good morning to everyone. I would like to welcome you all to the technical talk organized by the Department of Electronics and Communication Engineering in collaboration with Institution's Innovation Council of Techno College of Engineering Agartala on the occasion of World Creativity and Innovation Day. The topic for today's technical talk is going to be about the brain of modern electronics. Yes, it is about the semiconductor devices, from basic to advanced and its scope in industry. We are very honored and privileged to have with us today Dr. Ankur Devnath, Staff Engineer of Western Digital, as an esteemed speaker. Before we begin, may I request our principal, Dr. Debakar Dev, to please share his valuable insights. Is going to be about the brain of modern electronics. Yes, it is about the semiconductor devices, from basic to advanced and its scope in industry. We are very honored and privileged to have with us today Dr. Ankur Devnath, Staff Engineer of Western Digital, speaker. Before we begin, may I request our principal, Dr. Debakar Dev, to please share his valuable insights.
Hello, hello.
Hello? Can you hear me? Hello?
Yes,
Yeah, okay.
I will start.
এখানে একটু স্লো আছে। আচ্ছা, আমি
I'll
একটু
start.
বলে রাখছি, এখানে যেগুলো বলবে হয়তো তোমাদের একটু ডিস্ট্রাক্ট হবে, কিন্তু খুব ইম্পর্টেন্ট টপিক। যদি
I
কোথাও
would
বুঝতে
like
না
to
হয়
welcome
সমস্যা হয়
our
তো তুমি আমি
students
বুঝিয়ে দেবো।
and the special speaker today, Dr. Ankur Devnath. I would like to welcome all of you. And today's is from basic to advanced and its scope in industry. This is a very important topic in current time because the Indian government or we are also trying to develop our own semiconductor in our country. Today, the Department of Electronics and Communication Engineering, in collaboration with Institution Innovation Council, jointly organized this program. I would like to welcome and I would like to congratulate all of them for organizing this type of important technical talk and other topics covered in this technical talk: fundamental device, semiconductor material, PN diode, MOSFET, advanced device, 3D nanoflash, etc., and their scope in industry. Now we are using different electronic devices, and all the devices they must contain semiconductor or any chips, PN diode, etc. So this is very interesting topic, and I hope our students will get a scope to gather their knowledge from Dr. Ankur Devnath. I would like to welcome again Dr. Ankur Devnath, and I hope the success of this technical talk. Thank you all.
So, shall I start or?
Sure.
Yeah, so thank you, Mr. Divakar Dev, and good morning to all dear faculty members and my dear students in this technical talk. Okay, so my name is Ankur Devnath. So actually, it gives me immense pleasure to deliver this technical talk. Actually, just a minute, Dr. Priyansha is calling.
অ্যাকচুয়ালি এটা এখানে চলছে, এটা হচ্ছে শুধু একটা 3.5 জ্যাক হতে
Yeah, hello. Yeah.
কোনো তো ফ্যাকাল্টি এসে আমরা লাগবে গাইজ।
Yeah, so it gives me immense pleasure to deliver a talk, this technical talk in Techno College of Engineering, Agartala. So yeah, so let me start. So let me share the screen. Okay.
আমি একটা ট্যাগলাইন করেছি, সেটা কি করবো বলো তো?
So can you see my screen? Can anybody tell me? Hello. Can you see my screen? Hello.
হেডফোন লাগিয়ে রাখো।
Yes, sir. Yes, sir.
Okay, okay. Let me share again and I'll just tell you that, just respond.
কিছু বলার চেষ্টা করতেছে না।
You can see my screen, right? Hello?
Yes, sir.
Okay.
Yes, sir.
Okay. Yeah. Okay. So today, yeah.
Yes, it's visible.
Yeah. Yeah. Okay. Yeah. Okay. Thank you. Yeah. So today's technical topic is the semiconductor device from basic to advanced and opportunity in industry. So this is my brief introduction. So I am Ankur Devnath, and I did my PhD from IIT Madras and MTech from NIT Agartala. And my specialization is microelectronics or semiconductor device. Okay. And my present designation is Technology Development Engineer in Western Digital. So I am working in Western Digital actually. So So Western Digital, I think you know in the name of WD's passport. Okay, right. So you have hard disk, or you have also SSD, or you have pen drive, SanDisk pen drive, right? Or inside your mobile there is a memory card, right? We always talk about, okay, when we want to purchase some new mobile, right? So we generally we focus on two things. One is the RAM, how much RAM is there in the mobile, or how much memory size is there. Is it 32 GB, 64 GB, 128 GB? So more RAM, more storage, okay, if there, then the mobile, the operation of the mobile will be better. So we actually deliver this kind of product. So this is my agenda of this technical talk. Okay. So first, I will cover this. There's the fundamental devices. So it covers semiconductor material, p-n junction diode, and metal oxide semiconductor field level transistor. So in the semiconductor material, just first the first question come to your mind, that what is semiconductor, and why do we need this semiconductor, and where is the application, where we use actually. Okay, so I will cover this in this subtopic, semiconductor material, and then p-n junction diode. So I am assuming this p-n junction diode you already basic knowledge you have, because you have studied this in your intermediate level, that is in school. I think in modern physics in 12th standard, right? And also in first year, or maybe in third semester, you have studied this p-n junction diode. Okay, and MOSFET also you have, you know, in some extent, I think. Okay, so these are the basic devices. Okay, so thereafter I will just explain the advanced devices. Okay, here the two kind of devices are there. One is the gallium nitride high electron mobility transistor, that is HAM we call. Okay, this is the gallium nitride based HAM. Okay, so here I will cover what is the basic principal operation. Okay, and what are the advantages, okay, of this gallium nitride over silicon actually. Because nowadays whatever the technology, that semiconductor technology, most of the case we use actually silicon technology. Okay, the MOSFET, right? This MOSFET is also silicon technology. But why do we need this gallium nitride material, or gallium nitride based transistor? Okay, so that I will explain there. And then NAND flash memory device. Okay, so as I told right in the last slide, so we deliver a pen drive, right? Pen drive, then SSDs, okay, then a memory card, SD card, okay. So these all are in the family of NAND flash memory device actually. Okay, so these are actually called NAND flash memory, NAND flash devices. Okay, the technology name is NAND flash. And then I will explain. I will just give you the brief introduction, or the guidance. Okay, how you can go to semiconductor industry. So if you want to make your career in the semiconductor industry. Okay, so let's start then. Okay, so first is, what is semiconductor? Okay, so the first question can come to our mind, that what is semiconductor? Okay, and why do we use the semiconductor? Where do we use the semiconductor? Okay, so before going to that, I actually need to I will just classify the different material. Okay, so in terms of electrical conductivity, okay, so conductivity, you know, right? Electrical conductivity. Okay, so conductivity is how much current is flowing, that behavior of the current, that defines the conductivity actually. Okay, so in terms of electrical conductivity, whatever the materials are there in the world, okay, they can classify it into three categories. One is insulator, then conductor, and then semiconductor. Okay, so we know that already. We studied insulator, conductor, semiconductor. Okay, this is the basic, very basic level. Okay, but today I will just explain this kind of material. Okay, in terms of energy band diagram. Okay, so in energy band diagram is a very crucial part in the semiconductor. Okay, so if you are able to draw energy band diagram, okay, for any kind of semiconductor devices, so then your job is done. 80% job is done. You came to know all the basic understanding, internal behavior of the electrons, how electron is flowing from one terminal to another terminal. Okay, that you can understand if you are able to draw the energy band diagram. So energy band diagram is very important here. Okay, so I will explain the insulator, conductor, and semiconductor in terms of energy band diagram. Okay, so let's take first the semiconductor. Okay, since I will focus on the semiconductor in this technical talk. Okay, so here we can see, right. So this is the conduction band. There is so this is the, if I get it, this is the y-axis and this is the x-axis. X-axis is x, this distance, and y is giving you energy. Okay, okay. So you can see, right, there is a two kind of band here. One is conduction band, another is the valence band. Okay, which is also indicated by EC, that is conduction band energy, and there is the EV, that is valence band energy. Okay. So first of all, what is conduction band and what is valence band? Okay. So conduction band is where the electron is actually free. Okay. When the electron is free and it will be located in the band, that band is actually conduction band. Okay. And this electron, this free electron actually contribute to our current actually. Okay. So always remember that. Okay. So this is the conduction band where electron becomes free. Okay. And in valence band, electron is always bound. Okay, they are bound to another atom. Okay, there is a covalent structure is there. Okay, atomic level. So here I am not going to show this. Okay, so there is a structure, atomic level structure. We know that the electron will be covalent. There will be, two electron will make, okay, the covalent bond, right. So these electrons actually are bound in the valence band. These electrons are not free, and these electrons are not actually contributing to the current. Okay, and another important term is energy band gap. So this is the EG. It defines there is the energy band gap. Okay. So this is the energy band gap. Okay. So now if we compare, right, if we compare this structure with the insulator, okay, we can see, right, the energy band gap. Okay. There is a very important part. Okay. The energy band gap, that is the gap between the conduction band and the valence band. Okay. This energy band gap is higher than this energy band gap, right? So what is happening if energy band gap is higher? Basically, because of this higher energy band gap, it will block the electron. Okay, so it will block the current actually. So what is basically happening here? So if I suppose draw one energy band diagram, okay, for semiconductor I'm telling, and this is my EC, and this is my EV. Okay. Now let's say this is conduction, okay, and this is valence band. Okay. Now you kept this material. Okay, this is the some semiconductor material, and this is the corresponding energy band diagram. Okay, so you kept this material at room temperature. Okay, let's say 300 Kelvin or you can say 27 degree Celsius. So what will happen here? It will, this material, this semiconductor material will absorb the thermal energy. Okay, so it is the thermal energy. Okay, absorb the thermal energy, and if this thermal energy is greater than the energy band gap, then what will happen? Electron in the valence band, I told you that these electrons are bound. So now the energy will absorb by the material, and the electron in the valence band will break the covalent bond and it will move the conduction band. Okay, and it will become free. Right? So that will happen in the semiconductor. Okay. Now if you come to insulator, since EG is higher, right? This EG is higher, right? So what will happen now? That this thermal energy will not have sufficient energy actually. So basically for insulator, this EG will be less than ET. So now what will happen? The electron will not break the covalent bond because the electron semiconductor material is not absorbing the enough energy, enough thermal energy. Okay, so electron cannot move. Okay, electron cannot go to conduction band for insulator, right? Okay, so this way, so as I told that when electrons becomes free, that will be in the conduction band, and this free electron will actually contribute to the current, right? Very high if you compare with the silicon energy band gap, right? So that's why the silicon dioxide is always insulator. It blocks the hole, right? Okay, so that is the insulator and the semiconductor. Difference between insulator and semiconductor. Now I'll come to conductor. Okay. So here, if we see the energy band diagram, in the the conductor, the conduction band and the valence band are actually overlapping with each other. So that's why there is no question. There is no need of energy band describing the energy band diagram here. That is ED. Okay, since they are overlapping, and there is no electron in the valence band or conduction band, because all the electron can easily move to conduction band if free. Okay, that's why we get huge current in the conductor. Okay, so these are the difference between insulator, semiconductor, and conductor. Okay, now the next question. These are the classification. So next question can come. Okay, so insulator, we know the current is zero. It blocks the current, but in semiconductor and conductor, right, we always get current, right? Semiconductor also we get current, in conductor is also we get current. But why do we need to use semiconductor over conductor? There should be some advantage, right, in the semiconductor. Okay, because we are getting current in both the case, right? The main advantage of semiconductor is this one. Okay, it has ability to modulate the conductivity by introducing the impurity. Okay, so impurity, if you, yeah, hello, have any question? Okay, I'll continue. So semiconductor, what will happen? Some extent you studied impurities. You can, if you recall, n-type semiconductor, right? N-type, p-type semiconductor, right? Using some, if this is a semiconductor material, we are introducing some material here. Okay, some impurity here, so that it will become a extrinsic. Okay, so that material, extra material apart from the silicon atom, that is impurity here. So by introducing that kind of impurity, the conductivity can be modulated. Okay, so that part I will explain in the next slide. Okay, so what is n-type, p-type, and in brief in terms of energy band diagram. Okay, and another thing is that semiconductor is very highly sensitive to the temperature. Okay, and also it's sensitive to external source. Suppose I am illuminating some light. Okay, I am not giving any external biases. Okay, to that semiconductor metal, but I am giving some light with high intensity. Then also the behavior of the semiconductor material will change. Okay, so this is the main advantage. Okay, it can modulate. We can modulate the conductivity of the semiconductor by introducing the impurity. So then next is there is different semiconductor material. Okay, so these are the silicon. Silicon we know, right? That silicon we always study. Hello. Hello. And another thing is, yeah. So these are the different semiconductor material. Okay. So the very well-known material is silicon material. Okay, that we know. In PN junction diode also, if we make silicon technology using silicon technology, then MOSFET using silicon technology we make actually. Okay. Then gallium arsenide and gallium nitride. Okay, these are the compound semiconductor. Okay, these are the compound semiconductor. Okay, so gallium arsenide nowadays it's a little kind of obsolete. So it's very less. We actually use actually. And then they come to gallium nitride material. Okay, so gallium nitride material, there are some advantages or features over the silicon actually. Okay, so that part also I will explain in the subsequent slide. Okay, so basically this gallium nitride material. Okay, so in silicon, what are the basic three application? Basic three application is, we can use it in the high temperature operation. Okay, we can use it in power amplifier, that is high power application. Okay, and we can use it in high frequency application. Okay, but if we use gallium nitride material, okay, over silicon technology, then we can actually amplify all these three application, that is temperature, then the power and the frequency. We can increase that. Okay, and then gallium nitride oxide and the silicon carbide. So these are the another two kind of semiconductor material. So these are the main advantage of this gallium oxide semiconductor silicon carbide over the gallium nitride is they have very high breakdown field actually. Okay, so that's why we can use them in the high voltage operation or high power amplifier. Okay, so these are the basic kind of material, semiconductor material. Okay, and then so where do we use this semiconductor? Okay, so almost in all consumer electronics, right? In mobile, okay, mobile. If you I already told, right? In mobile, right? So you have memory card, you have RAM, okay, you have that CPU processor, you have GPU, right? All these are in the semiconductor area, right? So we fabricate it, okay. So then laptop also, okay, laptop we use the as I told you, right? CPU, right? And then smart TV, car, in average car, right? Car, suppose in average car, let's say the car rate is 10 lakh, right? Okay, so the average car we use at least 1,000 to 1,500 IC chip, semiconductor chip in the car actually. Without semiconductor, we cannot actually marketize the car. Okay, so then refrigerator. Okay, and then automation sector. Okay, the automation sector is what. So if you go to a chemical factory, okay, or if you go in the any electrical factory, right? So there's a Palatana is there in Tripura, right? So where you will see a machine, right? Different very sophisticated technological machine. Okay, this machine is actually need this semiconductor IC chip to run this machine actually. Okay, so here also we need semiconductor IC chip. Okay, and also to support the artificial intelligence. So artificial intelligence we implement, it's a software. Okay, software kind of thing, not software, it's a kind of thing. But we need hardware for to support this artificial intelligence. So hardware we need what kind of hardware? Which is having high performance. Okay, the RAM we should have high performance RAM. The CPU we should have high performance CPU. Okay, and also the storage capacity. That also we need. So to support artificial intelligence, we need high performance, high reliability semiconductor IC chip. Okay, so these are the basic things. So here, if you have any question, then ask me. So I will go to next slide. So have you any question here? You need to understand anything. Okay, any no question, right? Okay, then I will move to the slide. Okay, so these are the types of semiconductor. Okay, so as I already told in the last slide, right? So we have actually two kind of semiconductor. Okay, one is intrinsic semiconductor, another is the extrinsic semiconductor. Okay, so extrinsic semiconductor is further divided into n-type semiconductor and there is the p-type semiconductor. Okay, so in an intrinsic semiconductor, we know that, right? In intrinsic semiconductor, the N is equal to P is equal to Ni. So N here stands for electron concentration, hole stands for hole concentration, and Ni stands for intrinsic concentration. Okay, so intrinsic semiconductor is always have equal amount of electron and hole. Okay, and that is equal to Ni. That is intrinsic carrier concentration. Now the question is how these electrons and holes are equal. Okay, in terms of energy band diagram, I will show. Okay, so similar diagram that I have explained in the last slide. Here also I'm just showing here. So conduction band, valence band. Okay, this is EC, this is EP. Okay, and this is the energy band gap. Okay, now I am assuming T is equal to 0 Kelvin. Okay, and here I am not applying any kind of bias. Okay, bias or voltage I am not applying. Okay, I am not applying any kind of voltage or biases. It is at equilibrium condition, and temperature I made it 0 Kelvin. There is low temperature. Okay. Now, as I said, right. So, what will happen now? This semiconductor material will not have sufficient energy to absorb, right? So there will be some energy, that is thermal energy. Since T is equal to 0 Kelvin, thermal energy is very low. Yeah, very low here. Okay. So the Eg is right, very, very greater than Et. Okay. So in this case, what will happen? The electron cannot break the covalent bond. Okay. And in this case, electron cannot move. Okay. Cannot move. Okay. Now, if I increase T is equal to 300 Kelvin, okay, that is at room temperature, for example. Okay. What will happen now? Same thermal energy would be greater than Eg. And now what will happen? The electron is moving, right? The electron is moving to conduction band. Okay. Then these electrons are free. Okay. These electrons are free, became free in conduction band. Okay. And in the meanwhile, same time, what will happen? The hole will be left behind. Okay. Equal amount of hole. Okay. So here, how many electrons? 1, 2, 3, 4, 5, 6. These are the 6 electrons. Okay. 6 electrons. So there is a 6 also. Equal amount of hole will also appear. Okay. So that's why this for intrinsic semiconductor always N is equal to P, and that is equal to Ni. Okay. The next is extrinsic semiconductor. Okay. So now there I told, right, the semiconductor conductivity of the semiconductor can be modulated by introducing the impurity, right? The impurity is actually this. These are the impurity. Okay. So I have taken it from periodic table. That's why it's the 5th element and third element. Okay. So for n-type semiconductor, if we see, so phosphorus, arsenic, and antimony. Okay. These are the materials that we can introduce as a impurity to a intrinsic semiconductor. Okay. And then for p-type, we can use this boron, aluminum, gallium, and indium. Okay. These are the kind of material that we can introduce in the intrinsic semiconductor, and then it will become a p-type semiconductor or extrinsic semiconductor. Okay. Now we will understand what is happening inside the this kind of device, inside n-type semiconductor or inside the p-type semiconductor. Okay. So same thing. Okay. So this is a conduction band, valence band, EB and EC. Okay. And this is the energy band gap. Okay. Energy band gap. And same thing, T is equal to 0 Kelvin. Okay. Now, if you compare this diagram and this diagram, here what is happening? Here we don't see any kind of extra energy level in the energy band gap, right? But here we see, right? This energy band gap, this energy gap, not band gap, this energy gap we see. Okay. So this is the energy level. Okay. So this energy level, it is called the donor energy level. That is ED actually. Okay. So this is the ED. This is the donor energy level. Okay. And the gap between this conduction band and the donor energy level is, we can see, right? This is the gap between conduction band and valence conduction and donor energy level. Okay. So this is very small, right? As compared to EG, right? So when we are actually introducing impurity in the n-type semiconductor, this kind of impurity generally donor type of impurity. Okay, they always donate the electron basically. Okay, this kind of impurity in the n-type semiconductor. Okay, so here since this is the energy level actually. Okay, so energy level you can see, right, these are the electron. Okay, all are electron occupied in that particular energy level. Okay, now what will happen at T is equal to 50 Kelvin? Okay, I am not increasing directly to 300 Kelvin. I am increasing in a small step to is equal to 50 Kelvin. Okay, so what is happening here? So now, since I told you, right, since the energy gap in this between EC and ED, this energy level and conduction band is small energy gap means we need small temperature because we need a small energy, right? So with this 50 Kelvin, what is happening? The electron is actually moving to conduction band from this donor energy level actually. Okay, this electron, and this electron is actually because of that donor impurity. Okay, So here we don't see any kind of valence band to conduction band electron movement, okay, because the 50 Kelvin is there, very low temperature, and we need high energy, okay, for this transition from valence band to conduction band. But we don't need high energy, we need only small energy to transition between ED to EC, okay. So these are the electron, okay. Now if you see, this is the positive charge immobile ion. These are called positive charge immobile ion. When electron is actually moving from donor energy level to conduction band, the positive charge immobile ion will left behind actually. Okay. And now if we increase T is equal to 300 Kelvin, what is happening here? Now let's say whatever the impurity are there in the material, all are ionized, means all electrons already moved to conduction band, okay. Now there is no impurity ionization here, okay. There is no electron left in the donor energy level, okay, even if we apply or increase 300 Kelvin, okay. So now at 300 Kelvin what is happening? The valence band to conduction band transition is happening, okay. You can see, right, this transition, okay. Okay. So what is happening now? You can see, right? Here the number of electron, right, is increasing, right? And this electron includes what includes this electron? One is this electron is due to band-to-band transition, that is from valence band to conduction band, and another thing is that this electron is due to the transition between donor energy level to this. So that the electron is actually higher in number as compared to hole, okay? This hole. If there is a, for example, if there is a 10 electron, here is only 6 electron, right? So that's why the N is actually greater than P for N-type semiconductor. Okay, we can see in the energy band diagram, right? The number of electron is higher, okay, in the conduction band, okay, as compared to the holes in the valence band. So that's why always in N-type semiconductor, the majority carrier is electron and the minority carrier is hole, okay. So now the same thing will happen for p-type. Here instead of this kind of material, okay, we are using this kind of material now, boron, aluminum or gallium or indium, okay. Let's say we are introducing boron to the semiconductor material, okay, increasing semiconductor material, and it will become a p-type, okay. So this material is actually acceptor type in nature, okay. So acceptor type in nature means this will accept the electron actually, okay. So, so here what is happening? Same here in case of donor impurity, we have a donor energy level just near to conduction band. But in case of p-type, we have acceptor energy level. This is acceptor energy level, which is just near to valence band. Okay, same thing actually. So now again, this is the T is equal to 0 Kelvin. There is no transition. And when I increase T is equal to 50 Kelvin, okay, T is equal to 50 Kelvin. What is happening now? Since it is accepting electron, so it will accept. Okay, this electron, one electron is moving to this. Okay, and this atom will get negative. Okay, negative charge. Okay, same thing here also. One electron will move here and occupy this energy level. It will get negative charge. Okay. So this way we can see that the number of hole is already here. Okay, these are the number of hole, but still we don't have any free electron in the conduction band, right? Now if we increase the temperature to 300 Kelvin, now same at the end is equal to 300 Kelvin, what will happen? The band to band transition will happen. That is, the electron now will move from valence band to conduction band. Okay, and similarly, when the electron is moving from valence band to conduction band, the equal amount of hole will appear in the valence band. So here we can see that number of electron is actually higher. So P is greater than N here. So that's how we say, we say that in p-type semiconductor, the hole is majority carrier and the electron is minority carrier. Okay, and the impurity, right? These are the impurity, right? So this impurity is called as donor impurity. Okay, this ND. Okay, and this impurity is also called as acceptor impurity, that is Na. It's actually concentration, okay, per centimeter cube we can calculate, okay, per centimeter. So I think it's 2 into maybe 10 to the power 16 or around 17, okay. There also maybe it is around 2 into 10 to the power 16 or 17 per centimeter cube, generally we say, right? It's a moderate level of impurity concentration. Okay, so this N is donor concentration, Na is acceptor concentration. So in subsequent slide, this term will need actually. Okay, that's why I'm introducing this ND and Na. Okay. So here till now, you have any question? You can ask me. Okay, then I'll move. Okay. So now is PN junction diode. Okay. So I'm assuming you have some basic knowledge in PN junction diode because you have studied this. Okay. So you know, right? There are the two things. Actually, basically three scenarios there. One is equilibrium condition, another is forward bias condition, and another is reverse bias condition. Here I'm not showing reverse bias. I'm just focusing on equilibrium condition and the forward bias condition. Okay. So I already described, right? There is a P-type semiconductor and N-type semiconductor. Okay. So first of all, do you know what is equilibrium condition? What's the difference between equilibrium condition and the forward bias condition? Okay. So the equilibrium condition is when we are not applying any kind of bias. Okay, we are not applying. Okay, and the current. Okay, the current is always equal to 0. Okay, these are the two things that you should remember at equilibrium condition. The bias is bias we are not applying, and the current should be always 0. Okay, to maintain the equilibrium condition. Okay, so I will start from equilibrium condition. So I have P-type semiconductor and N-type semiconductor. Okay, now what is happening here? If I combine this P-type and N-type, okay, then it will be as PN junction type. Okay, now here you just should not think like that. That for sake of understanding, I am telling here I am combining the P-type and N-type. Okay, but in reality it is not happening. If you have P-type and if you have N-type, if you just attach that, the PN junction will not make. Okay, you cannot make PN junction in this way. There is a complex fabrication process is there. Okay, to make the PN junction diode. Okay, very much complex process, fabrication steps are there. Okay. So don't think like that. The P-type and N-type I can combine and the PN junction diode I can get. Okay. So so now this is the PN junction diode. Okay. So you can see, right. So what will happen in N-type semiconductor? So N-type semiconductor we know, right? The majority carrier is electron, and P-type the majority carrier is hole, right? So here I have indicated the electron is moving from N-type to P-type, and the hole is moving from P-type to N-type. Okay. So why it is happening actually? Because this is because of the diffusion process. Okay. So diffusion process, if you don't know, this part is actually called as junction. Okay. So now here what is happening, we see there is a positive charge and there is a negative charge. So if there is a positive charge and negative charge, what will happen? There will be electric field. Okay, there will be electric field. So this is the electric field profile, okay, for PN junction diode. There is a triangular shape. Okay, so how it comes, there is a big derivation in the if you just go to book, standard book, then you can find. Okay, you can see that there is a, it came from some derivation. Okay, there is a triangular shape. Okay, and this is the charge density profile. Charge density means this one. Okay, this positive charge and here is the negative charge. Okay, so this is the QND. It's called QND because this is because of the impurity. Okay, so ND we know, right? I have explained in the last slide. And this donor impurity concentration, Na is acceptor impurity concentration. Okay, so this is the corresponding charge density profile and electric field profile. Okay, so now we know that the electric field is there across the depletion region. Okay, this region. Okay, so whenever now I will show you the energy band diagram for PN junction diode, and this is the energy band diagram at equilibrium condition. Okay, so if you see there at this side, the energy level, right? The EC, the energy level is actually flat. Okay, this side also the energy level is flat actually, but in the depletion region, this is the depletion region area. Okay, depletion region area. Okay, the depletion region, if you see, the energy level is actually not flat. It's a, there is some inclination here. Okay, that is a slope. Okay, so whenever you see the slope in the energy level, then you will correlate with the electric field, and that slope is actually because of the electric field. Okay, this electric field. Okay, so that's why there is a slope because of the electric field. Now if you see, then there is another thing. This one, the barrier for electron. Okay, so what is this barrier for electron? Barrier we know, right? The in simple meaning we know barrier. What is barrier? Okay, so barrier electron means it will restrict the electron to flow from n type to p type actually. Okay, since there is a barrier height here. Okay, further movement will stop. Okay, so what will happen now? So electron now will not move from n type to p type further. Okay, okay, it will not become a minority carrier concentration. Similarly for hole also there is a barrier for hole. Okay, barrier height. So hole also cannot move. Okay, it cannot move here. Okay, so hole will not become a excess minority carrier concentration at n time. Okay, so in PN junction diode, basically what is happening, the diode current, if we derive, that is because of this excess minority carrier concentration, excess electron concentration in the p type, and excess hole concentration in the n type. The diode current is actually derived from this. Okay, since at equilibrium condition these are not happening, the diode current is actually zero, we can say. And obviously it's a equilibrium condition, it should not be any non-zero value, it should be zero, right? Okay, so now if we come to forward bias condition, right? So you can see now here I am applying some forward bias voltage. Okay, so forward bias condition, what is the condition for forward bias? I have to apply positive at p type. Okay, and I have to apply at negative at n side. Okay, so that way we can make the forward bias condition. Okay, so here same thing. So the charge profile will be there, same here. Okay, the electric field is there. Okay, now if you compare this electric field, okay, this electric field and this electric field. Okay, so it's a small. This electric field is actually small actually. Okay, as compared to this. Okay, in forward bias the electric field is small. Why it is small? Because now what is happening? You are applying biases, right? If you apply external bias, there will be some electric field. Okay, external electric field. Okay, that is from positive to negative, and you have already another electric field. That's internal electric field or built-in electric field. That is from this one. Okay, this is internal electric field. Now this external electric field actually compensate this, or now will try to nullify this internal electric field. So the net electric field will reduce. Okay, the net electric field will reduce. Okay, that's why the electric field is in, you can say that it's a reduced as compared to the electric field in the equilibrium condition. Okay, so now if I come to energy band diagram, so here what is happening, since I have applied the VF, there is the forward bias voltage. So what is happening, the barrier height, okay, you can see the barrier height is lower as compared to, see, earlier it was this, Now it is reduced to the here. Okay. Now electron in the n type will have sufficient energy to overcome this barrier and it can move. Okay, and it will become a minority carrier electron concentration. And this is the corresponding profile. This is the corresponding profile. Okay, this is the minority excess minority carrier electron in the p side. Similarly, for hole, the barrier height is reduced and the hole is actually coming to n type, and the hole is actually becoming excess minority carrier in the n type. Okay, so this is the profile. Okay, so I told, right, the diode current is actually derived from this. Okay, it depends. Diode current depends on the slope of this excess minority carrier in the p type and n type. Okay, since we have this kind of profile for forward bias, we can derive diode current from this profile actually. Okay, so again I am telling this a big derivation, so here I cannot explain all these things. Okay, so you can go some standard book, semiconductor device book, you can find there. Okay, so anyway, I'll come to now this. So this is the our final diode current equation. So this is a well-known equation, we all know that. Okay, the diode current, this is the diode current, this is the reverse saturation current, this is the forward bias voltage. Okay, that this voltage. Okay, and this is the VT, that is the thermal voltage. Okay, and eta is the ideality factor. Okay, this is the eta, ideality factor. So I will come what is actually what impacts this ideality factor to this actually diode current. Okay, and then we also know the diode current equation, right? This is the ID versus VF. Okay, so and this is the cutoff voltage. Cutoff voltage is, we know, right? The cutoff voltage is the minimum voltage that have to be crossed. So the VF should be greater than VC. Okay, to get the diode current. Okay, otherwise it would be zero. Okay, in this case it will be zero below the VC. So that we also know it is that it's exponential in nature, the diode current. Okay, but now this is in linear scale, right? Now if I want to plot this current equation, okay, in the log scale, okay, now the thing is different, little bit different, right? The same curve I am plotting in log scale. So but the current equation is little bit different, the character is little bit different. Okay, okay, so the first question can come, the why we are moving from linear scale to log scale. Okay, so these are the very important phenomena. Okay, in the semiconductor device. Sometimes, or in not sometimes, in many times, we have to plot the log scale. Okay, for any kind of device, for any kind for to plot the device characteristics for any kind of device, semiconductor device. Okay, so why? Because see here, if you see the current is showing zero here, if in this region. Okay, this region, when the VF is less than VC. Okay, the current is zero. But in this case, when VF is less than VC, okay, the current is actually not zero. Okay, it's actually there is some current, and this current is actually very small. Is in maybe in microampere or in nanoampere. That's why it is unable to show in the linear scale, but you can see in the log scale. Okay, so so why do we need this? So we need to understand in the better way actually. Okay, so here we can see, right, the eta, that is the ideality factor. In this case the ideality factor is 2. In this region, that is this region. Okay, the ideality factor is 1, and this region, okay, the ideality factor is again 2. Okay, so if you want to model this diode current in better way, or if you want to explain this diode current in better way, we have to plot the log scale. Then only we can get the appropriate information here. Okay, so we can see, right, there is a recombination effect is also there. Okay, then there will be a current. Okay, this current is nothing but this current. Okay, this plot. Okay, and then if you go higher voltage, okay, then this current is actually degrading. Okay, the increasing rate of the current is reducing. Okay, here I am not explaining the low level injection, high level injection, because uh, I need to explain another thing, so I don't have that much of time, but just wanted to show the curve. Okay, the difference when you plot in linear scale and when you plot the log scale, and the importance of the plotting in the log scale actually in semiconductor field. Okay, if you go and if you want to make career, or if you want to do MTech in the semiconductor, many times you have to do this plot. Okay, log scale in for any kind of semiconductor devices. Okay, So, do you have any question here in PN junction diode?
Yes, sir.
Yeah, tell me.
Sir, you were talking about biasing. So, what is exactly the process of biasing?
Yeah, biasing is nothing. Bias is nothing but voltage. Okay, bias is nothing but voltage. Okay.
Okay,
First of all,
sir.
bias is nothing but voltage. Okay. So VF is applying. So this VF is nothing but I am at bias. If VF is equal to zero, the bias I am not applying any kind of bias. That's it.
Okay, sir.
Yeah, you can mute. Noise is coming.
Hello? Yes, sir, it's okay.
Yeah, mute it. Noise is coming. Yeah, thank you. So, have any question here? Okay, then I will move to next slide. Okay, so now the MOSFET comes. Okay, the MOSFET. Okay, so before going to MOSFET, we need to understand the MOS capacitor. Okay, what is MOSFET actually? MOSFET means metal oxide semiconductor field effect transistor. Okay, so why metal oxide semiconductor? First of all, I will explain this. Why metal oxide semiconductor? Because we are using the structure is telling itself actually. This is metal. Okay, if this is the standard structure of the MOSFET. Okay, so this is metal. This is insulator or oxide we can say. Generally we use silicon dioxide here, SiO2. Okay, and then this is a semiconductor. Okay, so that's why it is a metal oxide and semiconductor. And why it is field effect transistor? Because the current, okay, uh, the current behavior, okay, the electron behavior actually it's because of the field effect, electric field. Okay, the electric field is there. I am applying Vg. Okay, Vg is controlling inversion layer. There is some electric field in the insulator. Okay, and there is some electric field from drain to source. Okay, that is actually deciding the behavior of the electron. Okay, the movement of the electron between source to drain or gate to semiconductor like that. So it's a field effect. Field is affected here. Okay, that's why it's a field effect transistor actually. Okay, and now before going to MOSFET, okay, so here just this is the drain side, this is the gate side, and this is the source side. Okay, so drain means what actually? So typical structure is this actually. If you see, okay, this is the symbol. Okay, so this gate, this is drain, and this is source. Okay, so now what is happening actually? So gate is actually suppose you have some how to enter. So gate is basically controlling the electron. Okay, so electron in this actually. Yeah. Okay, this electron is responsible for drain current actually. It will help to move from. It will help to flow the drain current from drain to source actually. Okay, and this drain is actually collecting the electron. If the electron will come here and it will collected by the drain. Okay, and the source is actually source of electron. Okay, okay, the source of the electron source is here. The electron will start moving from this side. Okay, okay, and it will move through this. There is an inversion layer here. Okay, the inversion layer is nothing but the electron concentration here. Okay, there is some path here in this case. Okay, the electron from source side will move, okay, through this inversion layer path, and it then once it is reaches to drain voltage, it will be collected by the drain. Okay, so this is the basic operation. I will explain in details in the next slide actually. But before going to MOSFET, we need to understand what is MOS capacitor. Okay, MOS capacitor means same thing: metal, oxide, and semiconductor. Okay, now here if you see, just a minute. Hello, can you see my screen? Hello, can you see my screen? Can anybody respond? Hello? Can you see my screen? Hello?
Yes, it's visible.
Okay. Okay, so so now I will explain the MOS capacitor. Okay, so there is nothing but metal, oxide, and semiconductor. So now I will just cut this area. Okay, this rectangle area. Okay, if I cut this area, then it will be on the metal, insulator, or oxide. You can also say, and then semiconductor. That is P type. Okay, and P type is Na. Okay, so here. So here, if you see, there is the okay. So this is the Tox means oxide thickness. Okay. So in MOS capacitor, okay, there is a three kind of region. One is accumulation region, okay, and then depletion region, and then inversion region. Okay. So one by one, I will explain. So what is accumulation region? So so first of all, to understand this region, I need to explain this threshold voltage. That is VTH. Okay, VG, you know that there's a gate voltage. This is the gate voltage. Okay. So first I need to explain the threshold voltage. What is threshold voltage is actually, so here you can see. Threshold voltage is the onset of inversion layer at which voltage actually. At which voltage the inversion layer will be onset, will become onset in the semiconductor at semiconductor in insulator interface. Okay, that voltage is actually threshold voltage. It means when VG less than VTH, generally we don't have current. Okay, there's a drain current, right? The current is approximately 0. Okay, okay, and this is a cutoff state, we can say. Okay, and when Vg is greater than Vth, okay, or greater than equal to Vth, then we have some current depending on the biases or voltage. Okay, we have some current. Okay, depending on the biases, Vg, Vd. Okay, so that's the threshold voltage. Means the threshold when Vg greater than Vth, the inversion layer will form here. Suppose this one. Okay, the inversion layer will form here in the insulator interface between insulator and semiconductor. Okay, just at the surface of the semiconductor. Okay, so now here in this case I am making Vg less than Vth because I am starting from this is the CV characteristic. Okay, since it is MOS cap, I need to plot also CV characteristic, right? So CV is the capacitor, y-axis is capacitor, and x-axis is VG, that is the gate voltage. So here only one voltage I am applying, no drain voltage, okay, no source voltage, only one voltage. I am focusing on gate voltage, okay, and this is the CV characteristic for this corresponding structure, okay, okay, these three structure, okay. Now I will explain the what is accumulation region, depletion, and inversion region one by one using this CV characteristics, okay. So first I will start from this region, okay. So here what is happening? This is the VG, right? So this is the negative region of operation, and this is the positive region of operation. Okay. So So this region is corresponding to this structure. Okay, that is accumulation region. So what happens in the accumulation region actually when VG less than VTH, and this is the VTH. Okay, so this area is VG less than VTH. Okay, and also if you see, okay, this area, so this one, okay, and this area also VG less than VTH. Okay, so now I am talking about only this region. Okay, accumulation region. So what is happening since I am applying VG, right? Negative VG, okay, negative bias or negative voltage. So here what will happen? The negative charge will appear at the gate side. Okay, you can see, right? Negative charge. Okay, these are negative charge. Okay. So now one thing you should know that whenever we have, okay, if you know the Gauss law also, from that using that Gauss law also we can describe. Okay. So whenever you have some negative charge in any material, suppose you have some object, okay, and you have negative charge, okay, you have negative charge. So there should be a positive charge, okay, to compensate this negative charge actually. Some object should be there, okay, to compensate this negative charge. Okay, this is actually a Gauss law actually. Okay, so similar to actually this should to maintain the charge neutrality condition. Okay, always negative charge is there, then positive charge should be there to maintain the charge neutrality condition. Okay, the term is charge neutrality condition. Okay, if there is a positive charge, okay, if there is a positive charge, there should be a negative charge object which can compensate this positive charge to maintain the charge neutrality condition in every material, okay, in the world. Okay, charge neutrality condition should be maintained in every material. Okay, equal amount of positive charge is there, then equal amount of negative charge should be there. Okay, so that's the concept here. So if I apply negative charge in the VG at the gate side, okay, then there should be a positive charge. Okay, now how positive charge will come? Okay, and what's the source of the positive charge? This hole is the positive charge. Okay, hole. Okay, since it is p type, the majority is hole. So hole is actually compensating. Hole is coming from this p type, and hole is compensating this negative charge. Okay, so that's why the hole is actually, you can see the hole is actually occupying this surface of the semiconductor. Okay, so there is no electron here. Okay, there is only hole. So that's the accumulation region. Okay, now if we compare this metal and semiconductor, again in between there is semiconductor insulator, right? It's just a parallel plate capacitor, right? This is metal, this plate is semiconductor, and in between what is the insulator? This is insulator. Okay, it's just a parallel plate capacitor we can compare. Okay, so what is happening here? The corresponding capacitance should be Cox. Okay, and this Cox is this actually, this one. Okay, so this Cox is this one. So in the accumulation region, this Cox is flat actually because it's a constant, because there is no voltage dependent here. Okay, now I'll come to depletion region. Okay, so if you now here, this is the depletion region actually. This is this part. Actually, this is the depletion region. Okay, so here also we can see, right, VG still less than VTH. Right? So VG less than, still less than VTH. Okay, now what will happen? This is the VG less than VTH, still under cutoff region. No inversion layer is forming. Still no inversion layer in this area. Okay, in this area, no inversion layer. Okay, now if I increase VG, okay, I am increasing VG, right? Yeah, in the capacitor CV characteristic, I am increasing VG. Okay, if I increase VG now, and the VG is positive now, okay, what will happen is this is the positive, right? This positive charge instead of negative, now it's a positive. Okay, what will happen? So we know that, right? Positive will always repulse, right? So when I am applying positive here, the hole will be repulsed by this positive charge. Okay, so hole will move this way. Okay, in this case. Okay, when hole is moving, the always electron. If electron is moving, the electron will always electron is moving from the atom, right? The left is leaving the atom, then the atom should become a positive charge. Okay, similar thing for hole. When hole is moving, then the atom it should be become a negative charge. Okay, so this is the negative charge will appear. Okay, all are negative charge. Okay, since hole is actually repulsing here, so negative charge is here. Okay, so this is actually called, this region is actually called again, you can say depletion region. Okay, again it's like a PN junction. Okay, depletion region. Okay, the more depletion is the MOSFET, you can say. Okay, so now here I am applying positive charge, right? These are the positive charge, and this positive charge, now I told, right, if there is a positive charge, there should be a negative charge to maintain the charge neutrality condition. Okay, so this is positive charge and there should be negative charge, and these are the negative charge to compensate this positive charge. Okay, okay, so now in accumulation region there is one capacitor only, Cox, but in case of depletion region there will be another capacitor. Okay, that will be connected in series with Cox. Okay, and this Cox, this CS, that is semiconductor capacitor also you can say, or depletion capacitor also you can say, this CS is actually corresponding to this. Okay, okay, and if we connect these two capacitors in series, basically it will reduce, right? So that's why it is reducing. Okay, in this case it's reducing as Vg is increasing. Okay, up to here. Now in this case Vg is greater than Vth. Okay, now what will happen? See, the inversion layer is actually forming at the surface of the semiconductor. Okay, so here I am even increasing, further increasing the Vg, that is the inversion region. Okay, the Vg greater than Vth. Still it is a positive. Okay, now what will happen? The electron, since it is a higher gate voltage, okay, gate voltage is higher. Now instead of hole, here hole, sorry. So what will happen? The electron from the p type. Okay, now you will say, where is the electron? This is a p type, because but electron is the minority carrier in the p type, right? So that's the source. That's the minority carrier electron is the source of this electron actually. Okay, the electron will come from this minority carrier, or we can say these are the minority carrier concentration only, electron concentration in the p type. Okay, this electron will actually generate, these are thermally generated electron. Okay, and this electron will come here actually, and it will stay here at the surface of the semiconductor. Okay, and this positive charge will now compensated by this electron. Okay, and again, since there is again here there should be a negative charge. Okay, there should be a negative charge. Okay, still there will be negative charge. Okay, but now electron concentration is very high. Okay, the electron concentration is very high in this case, so that's why this positive charge is actually compensating only by this electron, not by this negative charge actually. Okay, so the corresponding capacitor will be Cox. Okay, so again it is actually, if I see the capacitor CV characteristic, then again it is increasing, and it's actually Cox. Yeah. Okay, so this is the basic MOSFET structure, MOS capacitor operation. Okay, so three region: accumulation, depletion, and inversion region. So this is the corresponding energy band. I will not go, but if you have question, then you can ask me. Yeah. Okay, then I will just keep. So this is the MOSFET operation. Okay. So now we understood, right, what is MOS operation. Okay. So that is only based upon the gate voltage. Now I will introduce the VD and VS. Okay. Okay. And now this three diagram I will look into first. This three diagram, this three structure. Okay. And this is the corresponding ID VGS characteristic. Okay. First in this flow. Okay. First this, then this, and then this, and then yeah. Okay. Now this is the cutoff region, right? You see, this is the cutoff region. The cutoff region, what is cutoff region? When Vg less than Vth. Okay. So which region are in Vg less than Vth? Accumulation region and depletion region that we saw in the MOSFET, right? In the last slide. So here now what is happening? I am applying Vd equal to 0, still V is equal to 0. Okay. So there will be a depletion region. Okay. And Vg is here positive actually. Okay. And the negative charge will appear. No inversion layer. Okay, in this case, in the cutoff region, so there will be no current actually. Okay. Now, if you see here, so here the current, since there is no current, so this region actually. We do not see the current. The current is zero. The drain current is zero. Okay. So this region is VGS greater than VTH. Okay. And this VGS less than VTH. Okay. Now here on state region, okay, or onset of inversion. Okay, since Vg is now greater than Vth, there is an inversion layer. Okay, you can see the electron is here. Okay, where is the source? The electron is coming from here. The minority carrier electron is nothing but a minority carrier electron. Okay, inversion layer. The electron in the inversion layer is nothing but a minority carrier electron. Okay, at Vg is greater than Vth, and it is on state region. Okay. Now again I am applying a Vda equal to 0 and Vs equal to 0. Okay. Okay, so if I am applying Vd equal to 0 and Vs equal to 0, still there is that no drain current, because I am not applying any kind of bias at drain side and source side, only VGS. Okay, because the drain current is actually moving from this side to this side, right? Drain to source. Since there is no bias, the current is 0. Okay, similar thing. Okay, so even VGS greater than VTH. Okay, and I do not apply VD and VS, so current is 0. Now here is the scenario, the separate scenario. So now what I am doing, I am keeping this VDS at some constant voltage. Okay, let's say 5 volt. Okay, it's a constant. Okay, so this ID versus VG is also VDS is constant. Okay, and now what I'm doing, by keeping VDS constant, I'm increasing this VGS, and VGS is greater than VTH. Okay, the curve you can see, this is the curve actually. This is the curve what I'm seeing. This is the curve VGS greater than VTH. Okay, and we can see, right, the inversion layer is formed. So when inversion layer is formed, basically it is giving a path to flow the electron from source to drain actually. Okay, the electron will flow from source to drain like this. Okay, okay, and they collected at the drain side. Okay, so you know that the flow of electron or the direction of electron is just opposite to the flow of electron. Okay, the current will move from this way. Okay, through this path only. Okay, so this is the drain current. Okay, so this is the correct ID versus VGS characteristic. So here, if we increase VGS, then because the more VGS, more electron. Okay, and then more current. Okay, so that's why as VGS increase, the ID is actually increasing in that way. And now, if we now here there's another three structure. One is linear region. Okay, and then just before saturation region and saturation region. Okay. So here we can see, right? So it will describe this characteristic actually. ID versus now VDS. Instead of VGS, here what I'm doing, I'm keeping VGS constant. Okay. In this case, VDS constant. In this case, VGS constant. The gate to source voltage is constant. Okay. So here now I'm got a VGS constant and I am increasing VDS. Okay. So in smaller range, when the VDS is small, what will happen? You can see the curve is linear. Okay, this curve is linear. Okay, it's a linear. So that's why it is a linear region. Okay. Now if we go, okay, if we go to higher VDS, okay, higher VDS, okay, that is this case, just before saturation region. Then what will happen? The electron concentration will reduce at the drain side. Okay. So what will happen actually? Since it's a PN junction diode, right? It's a P and N. Okay. So the reverse bias